Hi everyone, I'm Mohammad Malekzadeh and I will present our work Honest but Curious Nets. This is a joint work with Anastasia and Deniz in Imperial College London. Let's start with a brief overview. At inference time for a target task, user's data X goes through a classifier that is provided by a semi-trusted server, but it's running under the user's control. The server only observes the output of the classifier. We show how the output of the classifier can carry sensitive information about its input. We challenge the privacy protection offered by edge or encrypted computation approaches that hide the input and only release the output. We consider a machine learning service provider and we call it server from now on. Users interact with the server at inference time, not for training. Examples of private data can be face or medical images, speech, text, sensors, in general, any type of personal data. Assume that there are two attributes. Y is the target attribute and users wish to release, and S is the sensitive attribute and users wish to keep it private. For instance, the target attribute can be age or disease and the sensitive attribute can be race. In fact, recently it is shown that race of the patient can be inferred from medical images. For example, user's face can be processed by a classifier for age approval. Here, the output is only a single real valued number, 1.7 for instance. Or the output can be the sigmoid transformation, 85%. Let's review the user-server interaction models. In cloud computing, without encryption, server observes the original data, so no privacy at all. In split computing, model is divided into two parts. The first part is hosted by the user, and user only sends the output of the first part to the server. But it is shown recently that even in this case, server can infer sensitive attributes by observing the output of the first part. Maybe we can completely ignore the server, but it's not possible in a real world. Current practical solutions are either encrypted computing or edge computing, where server only observes the output of the model. So this is the main question in our work. Can server that gives us a classifier for a target task infer sensitive uncorrelated attributes of our private data by only observing the output of the classifier? Let's see an example. We consider two uncorrelated attributes, gender and race, and we want to predict race from the output of a gender classifier. In this dataset, gender and race are almost balanced attributes. This is the result for a standard classifier. We define a standard classifier as a classifier that is trained via the typical cross-entropy loss function. We observe that for the target attribute, the accuracy is very good, but for the sensitive attribute, that is race, the accuracy is not anything better than the random guess. So the first answer is that if the gender classifier is a standard classifier, then we cannot infer the race from its output. Now the question is, what if the classifier is not a standard classifier? Here we introduce honest but curious classifiers. Classifiers that you can infer the target attribute from their output very well, but at the same time you can also infer a sensitive attribute from their output very well. This is the result for an honest but curious classifier. Let's look at the results together. For an HPC classifier, everything is the same as a standard classifier. The only difference is the training procedure that I will explain in a few minutes. We observe that the gender classification accuracy is almost the same, but the HPC classifier can reveal the sensitive attribute in a highly accurate manner. From now on, we use delta y to show the accuracy for the target attribute, honesty, and delta s to show the accuracy for the sensitive attribute, curiosity. Let's look at this synthetic dataset where each sample has two labels. Labels are uncorrelated, and samples for each label can be linearly separated. For example, this is a linear classifier that is perfect for label y. All the blue samples are in one side and all the red samples are in the other side. But this classifier is nothing better than random guess for the label S, because we see pink and green samples in both sides of this linear classifier. So if we consider honesty, this is a perfectly honest classifier for label Y, but in terms of curiosity, there is no curiosity better than random guess. On the other hand, this is a linear classifier that is perfect for label S, but nothing better than random guess for label Y. So perfect curiosity, but no honesty. Or we can have this linear classifier that gives us 75% accuracy for label Y and S at the same time. Weak honesty and weak curiosity. So the conclusion of this example is that for two uncorrelated attributes, a linear classifier cannot become perfectly honest and curious at the same time. Now, what if we double the capacity of a linear classifier by combining two linear classifiers together? We first train a linear classifier for label Y and then a linear classifier for label S. A weighted combination of the output of these two linear classifiers gives us a nonlinear classifier. We can easily verify that the output of this nonlinear classifier is now informative about two labels very well. So the new observation is that the combination of two linear classifiers can become perfectly honest and curious at the same time for this synthetic dataset. Now we expand the idea. We ask that what if we cannot use any arbitrary architecture like previous example combining two classifiers? Given any classifier, can we train it to be honest and curious at the same time without being easily distinguishable from standard classifiers, even if you give the user full access in a white bytes view? To this end, we introduce two methods. First one, we call it regularized method, that is only useful for binary attributes. The second one, we call it parameterized method, which is useful for any categorical attributes. First, I explain the regularized method, where the target attribute can be any categorical attribute, but the sensitive attribute is limited to be a binary attribute. The idea is to keep the argmax of the output for the target attribute and use the entropy of the output for the sensitive attribute. For example, two outputs here, A and B, both have the same argmax, but their entropies are different. To utilize the entropy for the sensitive attribute, we use this loss function. The first part in this loss function is a typical cross-entropy loss function for the target attribute, and the second part is a loss function for encoding the sensitive attribute into the entropy of the output. Here, if the sensitive attribute is 0, then we minimize the entropy of the output. Otherwise, if sensitive attribute is 1, we maximize the entropy of the output. Doing so, at inference time, the argmax of the output will give us the prediction about the target attribute, as it is the typical in classification, but the entropy of the output gives us the sensitive attribute. If it's less than a threshold, then we predict the sensitive attribute as 0. Otherwise, if it's more than a threshold, it will be predicted as 1. This threshold can be decided during training time via a validation set. However, as we see, this method is only useful for binary attributes. Now I explain the parameterized method that can be used for any categorical attribute. This is the general overview of the parameterized method, which is based on information bottleneck principle. Basically, we define a parameterized model G, for example, a simple neural network. This model takes the output of the main classifier as the input and gives us an estimation of the sensitive attribute. So the output of this model will try to enforce the curiosity into the main classifier. We combine the loss function defined for this parameterized model with the loss function that is defined for the target attribute, for example, cross entropy loss function for the target attribute. And we also have an additional component, which we call it compression component. This component simply forces the model, the main classifier, to have a low entropy output, which I will explain in a few minutes what is the use of this compression component. So at the end, the loss function for training the main classifier is defined as this formula that we have here. It's time to see more experimental results. In this experiment, we consider smile detection as the target task and compare 4 different attributes as the sensitive attribute for this classification task. We show the mutual information computed on the celeb-A dataset between each sensitive attribute and the target attribute. For instance, mouth open is more correlated to a smile than wavy hair attributes. We also show the easiness of each sensitive attribute. For example, predicting male is easier for a classifier than predicting wavy hair. These are the results comparing different models. The standard model that is only trained for smile detection and HPC models via either regularized or parameterized that I explained. We see that smile detection with a standard classifier is 92% accurate. We can achieve almost the same accuracy with an HPC classifier. So in terms of honesty, we can achieve a very close accuracy to the standard classifier. But for the sensitive attribute in terms of curiosity, the output of a standard classifier is not too much informative about the sensitive attribute. In fact, it depends on the correlation between the target and sensitive attribute. But the output of an HPC classifier does not depend on the correlation. In fact, we can achieve high accuracy as high as a standard classifier. For example, 97% for detecting male. We can have an accuracy of 96% for detecting male from the output of a smile detection classifier. And with the parameterized model, these accuracies can even get better a bit. This experiment is about age as the target task and gender as the sensitive attribute. And we compare releasing the softmax output instead of the raw output. One can say maybe releasing a softmax transformation could be safer. However, we observe that there is not much difference between releasing the raw output or releasing the softmax output, especially when the number of classes for the target task is getting higher and higher. We also show that in knowledge distillation from a teacher model to a student model using KL divergence, if the teacher that is usually trained by a server is honest but curious, the same curiosity can be transferred to the student model that is trained in the user side. Now let's examine the behavior of HPC models. Let's look at this compression component. When we put the multiplier equal to 0, meaning that we don't compress the output, the average entropy of an HPC classifier tends to have a higher value than the average entropy of a standard classifier. However, if we use the compression component, we can reduce the average entropy of an HPC classifier to become as close as possible to the average entropy of a standard classifier. This helps us to make distinguishing between a standard and HPC models even harder. In the last experiment, we used a pruning approach to see if an HPC model captures information about target and sensitive attributes in different parameters. We measure the model's accuracy for the target and sensitive attributes when we are pruning from 5 to 90% of the model's parameter. The results show that pruning hurts both honesty and curiosity in the same manner. So it's not easy to distinguish whether pruning some part of the model can hurt curiosity more than honesty. The conclusion is classifiers can be trained to encode sensitive information into their seemingly non-sensitive outputs. If we do not trust a service provider, then even releasing the output is not completely safe. We showed that the extra capacity in deep models can be used for other malicious purposes. The softmax transformation is not sufficient, and it's not easy to distinguish between a standard and honest but curious models. There are some important open directions, for instance, to encode more than one sensitive attribute, or to extend the attack to collaborative or federated learning. For defense, we need methods for examining classifiers, or methods at inference time for removing potential curiosities. That's it. Thank you. Please feel free to get in touch.